Preparing for a software engineering at YouTube interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a video recommendation system for YouTube? I would separate recommendation into candidate generation and ranking. Candidate generation could combine collaborative filtering, subscriptions, trending videos, and embeddings, while a ranking model scores candidates using watch history, session context, freshness, and quality signals. I would pre-compute user features, cache popular results, and keep online ranking within a strict latency budget. Continuous A/B testing would measure watch satisfaction rather than watch time alone. Safety filters, diversity, and new user fallbacks are essential to avoid reinforcing narrow or harmful recommendations. While answering, cover candidate generation, ranking models, watch history, freshness, personalization, feature storage, offline training, online latency, experimentation, cold starts, safety constraints, and feedback loops. Question 2. How would you design a globally scalable video upload and processing platform? The upload service should issue resumable session tokens so interrupted clients continue without restarting. Completed files go to durable object storage, while metadata is written to a strongly consistent database. A queue triggers asynchronous transcoding into adaptive bitrate formats, thumbnail generation, copyright checks, and moderation. Workers should be idempotent, retry failed jobs with backoff, and expose progress status. I would replicate popular content across regions and use a CDN for delivery, accepting eventual consistency for derived processing states. Make sure to cover resumable uploads, object storage, metadata services, queues, transcoding workers, multiple resolutions, regional placement, ID impotency, retries, content checks, and eventual consistency. Question 3. How would you implement adaptive video streaming for unreliable networks? Adaptive streaming divides a video into short segments encoded at several bitrates. The player downloads a manifest, monitors throughput and buffer health, then selects the safest quality for each upcoming segment. Dash or HLS supports this model across devices. I would optimize the bitrate ladder for perceptual quality, cache segments at the CDN edge, and avoid aggressive upgrades that cause rebuffering. The key metric is smooth playback, so slightly lower resolution is preferable to repeated interruptions. In your answer, talk about HLS or dash, segmented media, bitrate ladders, buffer health, client-side adaptation, CDN caching, startup latency, rebuffering, and trade-offs between quality and bandwidth. Question 4. What data structures would you use to maintain YouTube's trending videos in real time? I would ingest views, likes, shares, and watch duration events through a partitioned stream. For each region and time window, workers could maintain approximate counts using sketches, then retain top candidates in bounded heaps. A separate ranking stage would combine velocity, unique viewers, engagement quality, and abuse signals. Event IDs enable deduplication, while watermarks handle late arrivals. Because trending results tolerate small delays, I would favor scalable eventual aggregation over expensive globally synchronized updates. Be sure to mention event streams, time windows, approximate counting, heaps, partitioning, deduplication, late events, regional trends, ranking signals, and consistency requirements. Question 5. How would you design a comment system that supports high write volume and moderation? I would partition comments by video ID, with a secondary strategy for exceptionally popular videos to prevent hot partitions. Each comment receives a sortable identifier, allowing cursor pagination rather than deep offsets. Writes enter a durable log, then moderation and notification consumers process them asynchronously. Deletions should leave tombstones so replies and audit history remain coherent. I would cache approved comment pages, rate limit abusive clients, and clearly expose moderation delays as eventual consistency. Focus on partition keys, threaded replies, pagination, abuse prevention, asynchronous moderation, deletion semantics, caching, notification fanout, rate limiting, and consistency expectations. Question 6. How would you build a reliable view counting system at YouTube scale? I would treat a view as an event requiring validation rather than incrementing a counter directly from the client. Events flow through durable ingestion, where fraud detection, deduplication, session rules, and privacy filters are applied. Stream processors produce near real-time estimates, while batch jobs reconcile authoritative totals. Sharded counters avoid contention, and idempotent event identifiers make retries safe. The interface can show slightly stale counts, provided the system communicates consistently and converges to validated numbers. Cover event ingestion, bot detection, deduplication, delayed validation, approximate versus exact counts, aggregation, idempotent processing, privacy, and user-visible freshness requirements. Question 7. How would you design search autocomplete for YouTube? I would build a compact prefix index containing popular queries, titles, channels, and entities, then serve suggestions from memory at the edge or nearest region. Ranking can combine frequency, freshness, user context, language, and personalization. A fuzzy fallback handles common typos without making every request expensive. Responses need aggressive caching and a very small latency budget. Safety and privacy filters must remove harmful, sensitive, or identifying suggestions before they reach users. In your answer, discuss prefix indexes, popularity signals, personalization, typo tolerance, latency budgets, caching, regionalization, safety filtering, and protecting the system from abusive queries. Question 8. How would you prevent duplicate video uploads while preserving user privacy? For exact duplicates, I would compute a cryptographic hash over normalized media and check it against an indexed catalog. Near duplicates require perceptual fingerprints across sampled frames and audio, followed by a more expensive verification step. Matching should trigger review or reuse opportunities, not automatic blocking, because edits and fair use cases create false positives. Fingerprints and access controls must protect private uploads. I would separate duplicate detection from copyright enforcement, since their policies and evidence requirements differ. Make sure to cover content fingerprints, perceptual hashing, privacy boundaries, false positives, encrypted processing, copyright workflows, metadata comparison, and the difference between exact and near duplicates. Question 9. How would you design a notification system for subscriptions and live events? When a channel publishes, an event enters a durable notification pipeline. Small channels can use fan-out on write, while massive channels should fan-out on read or process subscribers in batches to avoid write explosions. Preference checks, quiet hours, language, and device capabilities happen before delivery. Push providers require retries with backoff and deduplication keys. I would prioritize live alerts, apply backpressure during spikes, and expose delivery metrics without promising exactly once notification semantics. Discuss event generation, fan-out strategies, user preferences, push providers, batching, retries, deduplication, ordering, quiet hours, backpressure, and handling channels with millions of subscribers. Question 10. How would you investigate a sudden increase in video rebuffering? I would first verify the regression using rebuffer ratio, startup time, playback failure rate, and affected session counts. I would segment by region, device, ISP, app version, content type, and bitrate to localize the fault. Then I would compare deployment timelines, CDN cache hit rates, origin saturation, manifest errors, and player decisions. A canary rollback or safer bitrate policy can reduce harm while investigating. Traces and representative session logs should confirm whether the bottleneck is client, network, CDN, or origin. Be sure to mention user impact metrics, segmentation, recent changes, CDN health, origin capacity, bitrate selection, network geography, tracing, rollback strategy, and controlled experiments. Question 11. How would you build a low-latency live streaming architecture? I would accept redundant live inputs, segment them into small chunks, transcode an adaptive ladder, and publish low-latency HLS or dash manifests. CDN edges distribute chunks close to viewers, while a control plane tracks stream health and failover state. Smaller segments reduce latency but leave less buffering margin, so the player needs careful rate adaptation. I would monitor glass-to-glass latency, rebuffering, encoder health, and regional capacity, with automatic fallback to a conventional latency profile. Cover ingest protocols, chunked encoding, transcoding, packaging, CDN distribution, latency targets, synchronization, scaling, failure recovery, and the trade-off between latency and playback resilience. Question 12. How would you design a content moderation pipeline for videos and comments? I would combine upload time checks with asynchronous, multimodal analysis of video frames, audio, metadata, and comments. High-confidence violations can be blocked immediately, while uncertain cases enter prioritized human review queues. Every decision should record the model version, policy rule, evidence, and appeal state for auditability. Sampling and drift monitoring detect quality regressions. To minimize exposure, I would limit distribution before review, while allowing safe content to publish quickly and preserving transparent creator appeal paths. Focus on synchronous versus asynchronous checks, multimodal classification, human review, policy versioning, appeal workflows, queues, confidence thresholds, auditability, and minimizing harmful exposure. Question 13. How would you choose storage technologies for YouTube metadata, video files, and analytics? Video bytes belong in durable object storage because they are large, immutable, and retrieved through CDNs. User and video metadata may use a strongly consistent relational store where transactions matter, or a distributed key-value system for predictable, massive-scale lookups. Search needs a separate inverted index, and analytics belongs in an append-oriented warehouse or lake. I would choose based on access patterns, not popularity. Durability, latency, consistency, operational complexity, and lifecycle cost all matter. In your answer, compare object storage, relational databases, wide column stores, search indexes, data warehouses, access patterns, durability, consistency, scale, cost, and lifecycle policies. Question 14. How would you safely roll out a major change to YouTube's playback service? I would hide the new path behind a feature flag and begin with dark traffic or internal users. A small canary region would receive real requests while dashboards track playback success, rebuffering, latency, crashes, CDN load, and business guardrails. Automated rollback should trigger on predefined slow violations. I would expand gradually across devices and regions, compare against a stable control group, and review logs and traces before full release. This separates technical confidence from product experimentation. Discuss feature flags, dependency validation, canaries, staged regions, automated rollback, SLOs, experiment design, observability, dark launches, and guarding against metric gaming. Question 15. Describe an algorithmic approach to selecting the top K videos from a massive event stream. If events arrive continuously, I would partition them by video ID and maintain local counts within a defined time window. Each worker keeps a minute heap of its local top K, then a coordinator merges those candidates into the global top K for extreme cardinality. Count, min, sketch or heavy hitter algorithms reduce memory, followed by exact counting for shortlisted videos. Watermarks handle late events, and periodic batch comparisons estimate approximation error. The correct design depends on freshness, accuracy, and cost requirements. Make sure to cover streaming constraints, partitioned aggregation, heavy hitters, min heaps, approximate algorithms, mergeability, time windows, memory limits, and validation against exact results. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.